Welcome to the deep dive. Today, we're going to take a sledgehammer to the black box of a technology that is just radically changing everything.
Everything from hobby garages to global supply chain.
Exactly. It's 3D printing. And if you, like so many of us, have seen those videos of the machines working and just felt that, that deep curiosity.
I'm wondering how it all actually works.
Yeah, how does this magic happen? Well, what do all the acronyms mean? How do you even begin? Well, this deep dive is for you.
And it's really the perfect time to get this foundation. I mean, for too long, 3D printing has been kind of shrouded in this really technical jargon. It can feel so inaccessible.
It really can.
So our mission today is to filter all that for you. The articles, the primers, the tech comparisons, and just pull out the absolute essentials. We are giving you the vocabulary and the concepts you need to go from being curious to, well, being informed and ready.
Exactly, cutting straight to the core.
Yeah.
So let's unpack this fascinating world. I think we have to start with the most fundamental definition. Because once you grasp that underlying mechanism, everything else kind of falls into place.
It really does. So at its essence, 3D printing is, well, it's the process of creating a physical three-dimensional object from a digital blueprint.
Just a file on your computer.
That's all it is. But the true technical term for the method itself is additive manufacturing.
Additive manufacturing. Okay, and that single phrase, that defines everything, right? Mostly because it stands in direct opposition to how we've made things for, well, forever.
For centuries, yeah. The term additive means material is gradually added and joined together layer by microscopic layer until the final shape is formed.
Now contrast that with basically every traditional method we know.
Right, like machining or carving or drilling, those are all subtractive methods.
Subtractive. So we're used to seeing material taken away.
Hmm.
You think of a sculptor with a block of marble just chiseling away.
Or a huge factory mill cutting a block of aluminum. You start with this big chunk of material, and you remove waste until your object is left behind.
And the difference there is huge.
Oh, it's enormous. With subtractive methods, you inevitably create a ton of waste material shavings, dust, chips. With additive, you only put down the material you absolutely need.
And this is the critical part. It lets you build shapes that would be physically impossible if you had to start with a solid block.
Exactly. The sources give a really great way to visualize this.
Yeah.
If you take your digital 3D model and you just conceptually slice it horizontally into, say, thousands of hair-thin layers.
Okay, like a skeet scan.
It's a great analogy. The 3D printer's job is just to execute each one of those slices, one after the other. It's basically tracing the outline of that digital slice, then it moves up just a tiny bit and traces the next one right on top of the first.
So it's almost like drawing with a really, really precise hot glue gun.
That's it. And the key benefit, as you said, is that geometric freedom. You can create these internal channels or hollow spaces or complex mesh structures that, traditional tools just can't reach.
And while this all feels so cutting edge, so new, the history is actually older than a lot of people think.
Oh, far from it. I mean, the commercial explosion, that's really happened in the last decade or so.
Right.
But the fundamental concepts, they date all the way back to the 1980s. Key technologies like stereolithography, SLA, that was patented as early as 1986.
So it just took a while for the technology and the cost to catch up to the idea.
A classic case of innovation finally meeting affordability.
Okay, so that's the core principle.
Yeah.
Let's move on, because if you're shopping for a printer today, you're hit with a choice right away between two very different technologies.
Yes.
We have to talk about FDM and SLA.
These are the two a beginner absolutely has to understand. Your choice between them is going to dictate your cost, your materials, the complexity, and, ultimately what your final part looks like and does.
Let's start with FDM, or fused deposition modeling.
Sometimes called FFF, fused filament fabrication, same thing.
Right. And if you see a big spool of plastic string next to a printer, you are looking at FDM.
FDM is, without a doubt, the entry point for most beginners. And that's mainly because of its affordability and its simplicity. The whole mechanism is very straightforward. You have that plastic string, the filament.
Yeah, that unstools from a coil.
Exactly. And a mechanism called the extruder pushes that filament along a path.
And that path leads to the heat.
It does. It pushes it into the hotend, which is just what it sounds like. The plastic melts down, and then it's forced out through a tiny little opening.
It's a nozzle.
That's the nozzle. It gets laid down onto the build plate. The hotend moves around, and then the whole thing shifts up a little bit to start the next layer. It's robust, it's pretty clean, and it's easy to maintain.
Now, let's switch gears completely to the other main technology, SLA. Stereolithography.
Mm-hmm.
This is totally different. No heat, no spools.
Hmm.
This uses UV light and liquid chemicals.
That's right. SLA uses a vat of a photoreactive liquid resin. It's a liquid that solidifies really fast when you expose it to specific UV light.
So how does that work?
The machine submerges a build platform into the vat of resin. Then UV light, which in modern printers is usually projected through an LCD screen, it flashes the pattern of the current layer from below.
And that cures it, hardens that specific shape.
Precisely. The platform then lifts up just a tiny bit, lets fresh resin flow underneath, and then the process just repeats layer by layer by layer.
And the results, I mean, they really speak for themselves. You get incredibly fine detail with this process.
Far smoother surfaces, much higher resolution than FDM. But this is where we get to the trade-off.
The big trade-off.
And it's a significant one. While the detail is just its superior, the workflow is much more complex.
You're dealing with chemicals.
Liquid chemicals that require safety precautions, you need gloves, you need good ventilation, and the parts aren't even finished when they come off the printer.
Oh, right. There's post-processing.
A lot of it. They have to be thoroughly rinsed in alcohol to get all the uncured resin off, and then they need a final, complete cure in a separate UV chamber to get to their maximum hardness.
So, okay, let me push back on this a little. If SLA offers objectively better detail,
It does.
why do the sources unequivocally recommend FDM for a beginner? I mean, wouldn't someone who wants to print, say, D&D miniatures or detailed models, wouldn't they want that SLA quality right from the start?
That's a great point, and the answer really comes down to friction.
Mm-hmm.
And, well, initial investment. While SLA gives you that superior artistic detail, FDM is cheaper, it's safer, and it is so much faster to just iterate with.
Okay.
A beginner needs to learn the fundamentals, modeling, slicing, how the machine works, without adding the complication of chemical handling and all those mandatory post-processing steps.
With FDM, you can just print a replacement part for your vacuum cleaner and be done with it in an hour.
Exactly. Minimal cleanup. SLA is more of a specialized tool for those high-detail artistic applications. The advice is start simple, learn the system, and then if you find you really need that level of detail, you can consider making the jump.
That makes perfect sense. Master the mechanics before you introduce chemistry.
Well said.
Okay, so no matter which printer you're using, FDM or SLA, you cannot escape the jargon. To troubleshoot or buy materials or even just watch a tutorial online, you have to understand the vocabulary.
Let's nail down the critical terms, and let's start with that FDM hardware chain again, since that's what we're recommending.
Yeah.
We mentioned the filament, the raw material. What about the part that moves it?
That's the extruder. And this is more than just a little motor. It has to apply this incredibly precise force to the filament.
Right, to push it into the hot section at the exact speed you need, that consistent flow rate is critical for quality.
Okay, so if the extruder is the engine, the hotend is where the real magic happens.
It's the whole assembly with the heating element and all the thermal parts. It has to heat the plastic up super fast and then hold that exact temperature.
Too cold and it jams, too hot and it just oozes everywhere.
Exactly. And sitting right at the tip of that hotend is maybe the smallest but most influential piece of hardware.
The nozzle.
The nozzle is everything. It's the point of extrusion. For beginners, the standard is usually a 0.4 millimeter nozzle. That gives you a pretty decent balance between speed and detail.
And you can change that.
Oh yeah. If you want ultra-fine detail, you go smaller, maybe to 0.2 millimeters, but your print time just skyrockets. If you want speed and strength for a huge part, you might jump up to 0.8 millimeters. That decision nozzle size is the first true compromise a printer forces you to make.
Speed versus resolution.
Speed versus resolution, yep.
Okay, that's the hardware. Let's talk about the software, because the machine can't move without instructions. That instruction generator is called the slicer.
The slicer is your command center. It takes your 3D model file, it performs that slicing operation we talked about, turns it into thousands of layers.
And then it translates all of that, the physical movements, the temperature changes, the flow rates, into a language the machine can actually read.
And that language has a name, G-code.
G-code.
It's just plain text, really. It's a specialized language used to communicate with all kinds of CNC machines, including 3D printers. It's just a long list of coordinates and instructions.
Like go to X equals 50, Y equals 20.
Set hotend to 200 degrees, extrude 1 millimeter of material. The slicer generates this incredibly complex sequence, and the printer just blindly executes it, line by line.
Okay, let's talk about two critical concepts inside the slicer that you have to think about for every single print. First one is infill.
Right.
If you print a cube, you almost never print it as a solid block of plastic. Why is that?
3 reasons: cost, time, and function. Infill is the internal non-visible structure of your model. The slicer creates patterns inside the object like a grid or honeycomb shape.
So if you're printing something just decorative, it doesn't need to be strong.
Exactly. You might use, say, 10% infill. You'd save a huge amount of time and filament.
But if you're printing something functional, like a wrench handle that needs to take some real torque,
Then you might jump to 80% or even 100% infill to maximize the strength, and you just accept the trade-off. The print will take 5 times longer and use 5 times as much material. Infill is the perfect example of how 3D printing lets you engineer the inside of a part, not just the outside.
okay, our final term then is supports. The machine builds from the ground up, so why do we need temporary supports? Doesn't the plastic just lay down flat?
Only if there's a layer below it to catch it. Gravity is the enemy here. If your design has an overhang that juts out too far, imagine you're printing a lowercase letter T.
Ah, okay. The horizontal bar has nothing underneath it.
Nothing. And the hot plastic would just droop and fall down. You get this stringy mess that printers call spaghetti.
So the slicer is smart enough to see that coming.
It is. It automatically generates these temporary pillars or scaffolding underneath those areas. They're designed to provide a foundation for those overhangs.
And when the print is done, you just snap them off.
You snap them off. They often leave a slightly rougher surface that might need a little sanding, but without them, the print would just fail. Knowing when and how to use supports is a key skill.
Okay, we have covered a lot of ground here. We've got the core principle of additive manufacturing, we've landed on FDM as the starting point, and we've mastered the essential vocabulary. The groundwork feels pretty solid.
It is. We've moved from the what to the how. And that naturally makes you ask the question of why. Why is this technology so disruptive?
Right, now that you understand the language, you can actually appreciate the applications.
I think the most immediate and profound impact is in rapid prototyping and customization.
Explain that.
Well, before 3D printing, if an engineer needed a prototype of a new part, it could take weeks and thousands of dollars to machine one single test piece.
Right.
Now, they can design it, slice it, and have a functional test model on their desk in a few hours just using basic FDM. That speed, it just turbocharges innovation.
And that speed, that customization, it translates directly into fields that need unique solutions.
Absolutely. Think about medicine. The sources we looked at highlight these incredible strides in custom prosthetics. Every human body is different, right? And custom fitting a prosthetic used to be so expensive and slow. With 3D scanning and printing, you can create a perfectly tailored lightweight socket or brace that costs a fraction of the price and fix the person exactly. It can dramatically improve a patient's comfort and mobility.
What about bigger things? We hear about printing entire houses.
Well, it's not just buzz. I mean, yes, there are massive printers doing that, but on a more practical level, construction companies are using it for tooling on site.
What kind of tooling?
Custom jigs, brackets, mold inserts for complex concrete work, things that are structurally necessary but you just can't buy off the shelf. They can print them right there, tailored for that specific job. It's incredibly efficient.
It really brings it all full circle. The foundational knowledge is just understanding that a part is built layer by layer. That's what makes this custom one-off production economically possible.
You don't need a huge factory setup. You just need a digital model and the right machine. And that is the transformative power that this deep dive was designed to unlock for you. You're not intimidated by the extruder or the slicer anymore. You understand their purpose. You get the difference between FDM and SLA. This knowledge doesn't just prepare you to buy a printer. It prepares you to understand the vast potential of manufacturing custom, functional, transformative things in your own home or business.
So we'll leave you with this final thought. Knowing that 3D printing lets you create geometries and internal structures that are just impossible with traditional tools, and knowing you can pick a material for any specific task strength, heat resistance, flexibility, what is the most critical, functional, real-world problem you're going to solve first? The power for personalized manufacturing is now, quite literally, at your fingertips.